Welcome to this hybrid event arranged by the IET's Angling Coastal Local Network, which represents members in North Essex, Norfolk and Suffolk. Welcome to those of you in the local audience here at the atrium, and also to those joining via Teams from other parts of the UK and indeed globally. Now, I'm Kevin Foster. I chair the Angling Coastal Local Network, and I'll be your host for this evening. I'm delighted to introduce our speaker, Russell Davey. Russell is a principal network architect at BT. He holds a first-class honours degree in physics from Oxford and a PhD in physics from Strathclyde. He also holds an MSc in telecoms engineering. Russell worked for BT since 1994 on various aspects of optical fibre networking research and development, including optical access and core transmission. And he's been based throughout at BT Labs. Now, he's worked as transmission network architect since 2013. Russell is a BT Fellow, Chartered Engineer, and a Fellow of the IET. So, Russell, over to you.
I came to the event here in the spring where Roger Ward gave a good talk on the history of System X development up at Martlesham. So, in many ways, this is a follow-on from that, and I'm going to talk about another big development area up the road from us here at Martlesham, which was optical fibre. This is the first airing of a presentation I've been working hard on through the summer on this topic. Its next airing will be up at Martlesham, where in November it is the 50th anniversary of Her Majesty the Queen first opening site. So as part of that, I'm giving a talk on this topic. Now, as Kevin said, I only joined in 1994, so relatively recently. And most of what I'm going to be talking about was before I joined. So to learn about that, I've spent the summer speaking to, I think, about 20 people who were heavily involved, who all generously given up their time. But I tried to back everything up with something in writing. So having been given a verbal steer about something, I tried to find something either published or some internal documents. So that's the approach I've taken. But part of my motivation to present it here is I'm very keen to take feedback. So if I haven't got something quite right or I'm missing some key thing, I'd rather hear it tonight or in the coming weeks than in front of my management in November. So the key message really is that optical fibre is absolutely key to the internet, which we all rely on totally in our lives today. So the photos there are all sorts of things that we do every day, and today without the internet, these things would not work. And optical fibre is absolutely vital to all of that. I list here on the right there that map is my day job, which is the core transmission network, which connects together our top 100 exchanges with very, very high capacity optical pipes. And the key enabling technologies for those are listed in the box there. Single mode fibres, you need semiconductor transmitter and receiver at each end, optical amplifiers, coherent WDM, and all optical wavelength switching. I'll say a little bit about those as I go through the talk, and also the pioneering work that was done on them all at Martlesham. But fibre doesn't just connect our cities, it also connects our countries. So here's a map of the subsea fibre network. So optical fibre has made the world a much smaller place. So you can buy something from China today as easily online as you can from here in Ipswich. And in my work life, I regularly speak on Teams to people anywhere in the world. It really makes no difference. Optical fibre has made the world a smaller place. And increasingly, optical fibre goes to our homes. So OpenReach recently announced that their FTTP had passed 20 million premises. That was a couple of weeks ago. Other fibre providers obviously are available. It's a competitive marketplace. The aim is to build 25 million premises by 2026. This is a big investment. So 15 billion pounds is a number that's always been spoken about and still is spoken about. And the key enabling technologies for that, similar ones: single mode fibre, semiconductor sources and detectors, passive optical networks, and blown fibre. And again, all of these things, key innovations that were pioneered up the road, Martlesham. And finally, mobile. You might be sitting there saying, well, actually, I just access everything I do is on a mobile phone. that's wireless. What's optical fibre got to do with me? Well, it's only wireless from your handset to the mobile phone base station, which you can see on the right there. EE have 18,000 of those all around the country, and a third of them are directly connected to single mode fibre. Those that are not directly connected, there's a microwave radio link, which I think Andy Sutton's talking about in the next talk in a month's time. And very quickly they get onto optical fibre. So optical fibre, however you access the internet, optical fibre is absolutely vital to it. So what are the basics of an optical fibre system? So those of you over 55 will recognise here Busby from the early BBC TV adverts, and we see here Busby trying to transmit some information to, I assume, his mum at the far end. In those days, of course, that was a telephone call. So the basic idea is those electrical signals were converted to light using a light source. In practice, that is a complicated semiconductor component to go along the optical fibre to the far end, where there's a light detector, another complicated semiconductor components, and converted back to electrical so he can talk to his mum. Of course, these days, you know, that this often will not be telephony. This will be the internet or the video, or whatever you're doing with it. I'll talk a lot in the talk about megabits per second. So 10 megabits per second means that I'm turning the laser, the light source, on and off 10 million times a second to generate the sequence of binary digits, ones and zeros, that represent your Netflix or whatever you're doing. Your broadband at home will probably be tens, or in fact, they've increasingly hundreds of megabits per second. And a good quality video needs a few megabits per second. So, bit of very basic physics and history. So they work by something called total internal reflection. So we see here a laser pointer being directed through some milky water, and if you get the angle right, then all of it gets reflected back from the water to air interface. And Victorian scientists like Tyndall use that to show light being guided within a beam of water as something of a party piece. So if that works for water, the next logical step is to say, okay, well, it'll work for a piece of optical fibre. And the first practical application of optical fibres was to make optical gastroscopes to look down inside your stomach and what have you. And that was invented in the 1950s. Having taken that step, the next obvious thing is to say, okay, well, can we start to transmit information along optical fibres? And back then, you couldn't really, two main reasons. One, making the optical sources and receivers was still very, very difficult. But also the loss of these fibres was far too high. It only really worked over meters. And that changed in 1966, when Charles Cow and Hockham published the rather scary looking paper on the left, but their conclusions are more readable. I should say that Charles Cow was himself pretty local. He worked for STL at Harlow up the road from here. And his conclusions are basically saying that using optical fibres to transmit information is theoretically possible. You could get the impurities and so on out so that you could make a usable optical fibre. And he quotes a figure of 20 dBs per kilometre. He says that looks far from impossible. I'll come back to what that means and where it came from. So Charles Cow won the Nobel Prize for Physics in 2009 for this paper, but also for the work he did in subsequent years to evangelise about optical fibres and basically make them happen. Hockham didn't actually win the Nobel Prize. And I think he published the paper and then went off and did other things. It was Cow that got the optical prize and the Nobel Prize. And I think that was because of this evangelising. But he was not alone in that. So another key figure from the period is F.F. Roberts, who worked for Post Office Research. Of course, this was back in late 60s. So the move from Dollis Hill in North London to out here to Martlesham was only just starting. And really the Post Office labs were one of the first groups to get into optical fibre. So when Charles Cow gave his Nobel lecture in 2009, he says that the substance of his paper was presented at an IEE meeting in January 66. And he says most of the world did not take notice. The exceptions were Post Office and the UK Ministry of Defence, who both quickly got onto it. So this is a good success story for Britain. Britain first started moving optical fibre forwards. So within a year, there were 3 groups. There was STL in Harlow, there was a post office in North London, and also Southampton University were there from the start, and throughout remain we're a world-class institution in this area and remain so to this day. So this 20 dBs per kilometre target, what does it mean and where did it come from? So that basically means after a kilometre of fibre, you've lost 99% of the light, but you've got 1% left. You've just about got enough to do something useful with it. So where did it come from? Charles Cow doesn't actually reference it in the paper. So verbally, I was assured by Keith Beals that this target had come from the post office, which seemed believable because Harlow and Dollis Hill were just up the road from each other. Post office were the only telecoms provider in the country. Where else would he have got it from? But I did want to back things up in writing, and so I found this paper from 1977 that Roberts published actually just before he died, I believe. But that's where he says that this post office target of less than 20 dBs per kilometre was set early in '66 and quoted to all interested parties. And I think where that was coming from was that the electrical systems that were used at the time, they had repeaters every kilometre or two. And so if the fibre couldn't at least match that, it had no hope. So FF Roberts then got very busy in 1966 and 67, mobilising the UK on optical fibre. So I've seen an internal memo from the time that shows that in March '66, he essentially went on a tour of anybody he could find in the UK who knew about how to make low glass. You can list them there, you can read them there. And then very quickly set up contracts with 4 parties, so in particular STL, where Cow was working. So Post Office funded Cow to do this work, Barr and Stroud and Sheffield University, various companies knew about glass. He set up a consortium to move the thing forward. Also in '67, the Post Office labs made their first optical fibre. So a chap involved called Dick Dyatt wrote a paper referring back to this, but we've got Jeff in the room who I think I'm right in saying was present for this episode. So Dick Dyatt got a preform of glass made, tube of glass, and then heated it up. And these days, of course, this is done on a sophisticated tower and it's pulled and so on. But that wasn't available at the time. So there was a lady called Jackie in the room who happened to have her tennis shoes or something with her. And so to cries of "Run, Jackie, run," she ran the length of the lab pulling this fibre. Jack was there, he can confirm. It wasn't very good. The loss was 30 dBs per metre, so nowhere near the target FF Roberts had set. But BT continued to make good fibres until when I joined in the 1990s. But that's how it started. But people didn't immediately accept fibre as the answer. It's still, although it's been theoretically shown that the losses could be got down to the required level, still a long way to turn theory into practice. And in fact, these photos from the Post Office Journal in 1970 are showing what was the preferred solution at the time. So both the Post Office and also AT&T thought that the answer for connecting our cities together to support the required growth in telephone traffic was millimetre copper waveguides. So I have an example here. So this is what was being put in. Had to be very, very straight, and I believe it had to be filled with nitrogen gas. And so for that reason, obviously, if it had broken, it'd be very hard to fix. So it's put into steel ducting. So the cost of that, I dread to think, but that was where the world thought the industry was going. And it was actually a field trial of this between Martlesham and Wickham Market, which ran until 1977. I'll come to what stopped that. So the next key landmark for optical fibre was 1970. There was an IEE conference on trunk telecommunications in London in October, and most of the papers were about this. But there are a handful of papers on optical fibre, and in particular, Corning from America announced that they had made an optical fibre with a loss less than the target of 20 dBs per kilometre that FF Roberts had set for them. And at the end, there was a discussion, and the discussion in the room was, is the answer these copper waveguides or is it optical fiber? And most people said, well, it's copper waveguides, and they're much more advanced in their development. And Dick died at the post office, photo at the bottom right, and basically said, well, we can wait for the waveguide to be laid in the ground and then come along and fill it with optical fibers, which was fairly accurate to what eventually happened.
Yes.
So quite quickly, Corning took a sample of their fiber to post office labs, where it was measured, and it was measured to be 15 dBs per kilometre, so less than the target. The story goes that they were incredibly secretive and protective about how their fibre was made, so they refused to go to the lab. They refused to go to lunch. They refused to leave the lab to go to lunch, and every time a bit was cut off, which you have to do to measure the loss of something, they would very carefully sellotape it onto the drum. And then to the horror, they dropped a bit and spent ages trying to find it, and eventually reluctantly left. And of course, as soon as they're out the door, the post office people apparently looked very carefully and found it and sent it off for analysis. So in 2001, the IEEE dedicated what's called a milestone plaque in Corning, USA, to recognize this achievement. And associated with these milestone plaques, there is a web page, and there Corning themselves call out the fact that in 1960, members of the British Post Office, so presumably F.F. Roberts, came over and gave them that requirement. So Post Office, I think there's good evidence, set the world in the direction of optical fibre. A couple of slides now on a little bit of physics. I'm going to talk about wavelengths and nanometers a little bit. So light can be thought of as a wave. The wavelength is the distance between adjacent crests. Blue light's got a wavelength of about 450 nanometers. So a nanometer is 0.8 zeros and a 1 of a meter. Red is longer wavelength, is out to 650. Now the light I'll be talking about in telecoms is actually in the infrared. It's longer wavelengths than the red, so you can't actually see it. And we talk about 3 windows, and we started off in the early days in the first telecoms window, 850 nanometers, where the components could be made, and then through the couple of decades I'm describing, things moved to 1300 nanometers, and then state of the art now is at 1550. So I will talk about wavelengths quite a lot. I'll also now talk here about the structure of optical fibers a little bit. So they're a solid glass right the way through, and to make the total internal reflection work, to keep the light within the middle bit, which is the core, the outer bit, which is cladding, and the core are doped slightly differently, so the light goes at a different speed in the two. In a multi-core fiber, the core is larger, it's about 50 microns, so the rays of light can bounce along the core following various different paths, and that's a bad thing because the ones and pulses of light representing the ones and zeros, as they go along the fiber, they'll start to broaden, and eventually they'll start to broaden into adjacent time slots, so they'll stop it working. So that's called dispersion. It's a bad thing. Whereas if you make the core small enough and the light can only go straight down the middle, that's called single mode fiber. And yeah, okay. So both Cow's paper in '66 and the 1970 Corning breakthrough was single mode fiber. But through the first half of the 1970s, the world moved towards using multi-mode fiber, basically because it was easier to get the light in and it was easier to join. So glossing over 5 years of doubtless amazing innovation here to get from 1970s to 75. So there have been massive improvements in both the fiber itself and also the semiconductor sources and detectors. But by 1975, at the opening of the Martlesham Labs, and there was a demonstration of 8 megabits per second over multi-mode fiber. So the chap demonstrating to Her Majesty is John Midwinter. One of his son was going to come, but I don't think he's made of it. So certainly I've been in contact with him. Yeah, John took over from F.F. Roberts and led the optical research through the key decade from the mid-70s to the mid-80s. Unfortunately, passed away a few years ago, but I have been speaking to his family. So things move quite quickly now. In 1977, BT had it, the Post Office had their first field deployment of optical fibre. So this was multi-mode, and so from the labs at Martlesham to Kesgrave, there was 140 megabits, and then all the way to Ipswich there was 8 megabits per second. Corning made the fibre. By now they'd got the loss down to 5 dBs per kilometre, and the fibre was put into cables by BICC. I can't say this was a world first. I think it was early, but I think the Americans did get there a bit earlier. But it was the first time that in Europe that public telephone calls were carried over a fibre. Yeah, and John Midwinter wrote a paper around about 2000 looking back, and he calls this out as a key moment because this convinced the company that you could put these fibre cables, which perhaps were just things boffins at Martlesham played with, you could put them in real ducts under the roads that were full of copper cables, contrasting with these things that you have to keep very straight and keep in special ducts. So at this point, work on the waveguide, on the copper waveguides, did stop, but it carried on a long time. And I have to say, I genuinely feel for the people who'd spent their lives working on that. It must have been they've done nothing wrong really, other than put their hearts and soul into working something they believed in. So I genuinely feel sorry for them. So things continued to move very quickly. The following year, 1978, BT started deployment of multimode fibre. So it went out to tender for what's called proprietary optical line systems, poles. The point being, I think the cable and the equipment at the ends were from the same vendor, which is definitely not how we do things today because it's standardized. So 79 contracts were placed with 3 vendors. This is all very UK at this stage: STC, GEC, and Plessey. And you can see on the map there where some of the early systems were deployed. The first one being in the Midlands. Some of these are still out there. I stumbled on one of them in my day job a year or so ago, because they carry on working, is what it says. And in general, fibre equipment carries on working. But meanwhile, so BT and the world, in fact, were going seriously now down the path of multimode fibre. But then Martlesham challenged and changed that. Everyone I've spoken to through the summer is adamant on one thing, which is that Martlesham led the world to single mode fibre. So Mr. Payne there did some cost modelling, which said that if you could reach 30 kilometres at 140 megabits without any repeaters, then there were significant cost savings there. With the multimode systems, you had to have a repeater every 6 to 10 kilometres. So some of those had to go in manholes under the ground, so they had to be powered. Doubtless it was pretty wet down there, and there's active components down there, so they'd have been hard and expensive to repair. Whereas single mode fibre was lower loss than multi-mode, it was cheaper to produce, it didn't have that mode dispersion which limited the bit rate. But the big but was it was more difficult to get light into the fibre, and it was harder to splice. But the big decision was made, I've heard him described as the game changer, Sidney O'Hara, who was Deputy Director of Research, I believe, and he chaired an internal workshop up at Martlesham in the admin block, went round the table and asked people from the various components of the system, what was it then that was going to be the problem, and basically the decision that came out of that was we were going to go single mode. So at the time of the first Martlesham Open Week in 1980, there was a lab demo of what David modelled. So 37 kilometres, unrepeated, 140 megabits over single mode fibre. And again, impressively quickly, things moved on. So in 1982, the BT did the world first field trial of single mode fibre. That was between Martlesham and Woodbridge. And a key aspect of it was showing that single mode fibres could be jointed in a stripy tent by the road, which is what you can see in the left-hand picture there. I'm told that this was a race to be world first, but it was put on pause for a couple of days because they were working down a manhole, and a member of the public who was a bit of an animal lover wandered past and spotted a rare spider down the manhole cover, and apparently told the RSPCA, and so work had to stop for a couple of days while these rare spiders were removed. So never let it be said we don't take our corporate responsibilities seriously. Yeah, so you can read the bit rates there, 140 and 650 megabits per second. And there was also a second trial link deployed I think that was more the case. We sort of left STC more to that, I think. And I think that was probably key in that we could very quickly then move to deployments. So just the following year, in 1983, there was the first deployment in the world, commercial deployment of single mode fibre between Luton and Milton Keynes. That was STC. So on the right there, there's quite a nice article, I think written by STC, gives some details. But that said, it was a UK first. But I found the BT press release in the BT archives, and on the left that makes clear it was a world first, which is what I was verbally being told. So the world first commercial deployment was also in BT. And we should also not lose sight of the fact that Martlesham were world experts on the design and making single mode fibres. So in 1982, Jim Ainsley and Clive Day had the plenary paper at the big OFC conference in America, which whenever I had a paper at that occasionally over the years, I always tell people, oh, this is the Olympic Games of optical fibres. You know, I've won an Olympic gold medal now. But Jim and Clive didn't have any old paper. They were in the plenary. That's the first session right at the beginning where everybody sits there. And so they were invited at that time to give a plenary paper on the current worldwide status of single mode fibres, sort of showing the status that BT had at the time. And the sort of things they were doing was optimizing the doping levels of the fibre and the diameter of the core, and settling really on the design of fibre, which you can see in the graph here. This is from one of their papers at the time. So this is wavelength along here, this is loss, and you can see the sort of double dip, which is in all optical fibres that are deployed today, with a very low loss of 1550 of 0.2 dBs per kilometre, so 100 times better than the original FF Roberts target, and then a bit higher at 1310. So this is recognised with the Queen's Award in 1985. Okay, there was another Queen's Award in 1993, and that was for the semiconductor components that were connected to the sides, to the ends of the fibres. Thank you for Mike for helping me out with this. This was a technique called MOVPE, was worked on at Martlesham. So you can see there a picture of the equipment from the time, which apparently was made with the help of a local plumbing company. And this was, you know, worked on in a collaborative basis with universities and companies and so on. It was commercialized through a joint venture with DuPont. But this technique is widely used today to make the transmitters and receivers that are used in our optical systems, and a whole bunch of other things actually. So again, this won another Queen's Award for Industry in 1993. Okay, so yeah, where do we go now? So we can go 30 kilometers. What happened next? So I think the next big innovation was something called coherent. This is widely used in the network I design today. I can't begin to explain it properly here, but suffice it to say that this was the first time that we started to exploit the fact that light is a wave. So with all the previous stuff I'm talking about, you can think about Busby basically turning his torch off and on and counting how many photons got to the far end. Here, for the first time, the precise wavelength of the light, A, mattered, and B, was usefully used. And this had two benefits. So firstly, you could increase the reach, and secondly, using techniques that had already been used in radio transmission, things like something called QAM, you can get far more bandwidth down the fibre. So this is widely used in core transmission networks today, and won the Wright Prize Fund with some very compelling words you can read there. The work is a significant step in the continuing improvement of world communications and is a real benefit to mankind. I'll just pause at that point to say the chap second from the right is the technically brilliant and very nice Richard Wyatt, who was my first boss and unfortunately passed away a couple of weeks ago. So in 1988, BT did the first field trial, first deployment of coherent in the field. That took the reach to 176 kilometers at 565 megabits. My colleague Nigel Walker was very heavily involved in that and gave me this photograph of the equipment and so on. Yeah, so it's another significant step forward. And that coherent technique is now widely used in intercity transmission in the UK and worldwide, in combination with one other technique, or many other techniques, but another key one is erbium-doped optical fiber amplifiers. So these were a device, it was first reported by Southampton University in 1987. And the basic idea is that you take, having spent most of the 70s getting dopants out of the glass to make it as pure and low loss as possible, they started putting, in a very controlled way, small amounts of an atom called erbium into a length of fiber, about 20 meters. And then you pump it at a particular wavelength, and your weak signal comes in here from the left and gets amplified through the fiber, and so comes out much bigger at the far end. Last week I was at the ECOC conference in Denmark, and there was actually a dedicated 1-hour seminar on the history of the erbium fiber amplifier, because it was a significant development. And Southampton University today, Payne, not this Dave Payne, the other one, were presenting that and called out our own Tim Whitley as one of the top 10 contributors in the world to the development of the fiber amplifier. And that was specifically because Tim was the first to diode pump a fiber amplifier. Before that, you needed a great big gas laser, something that you wouldn't fit on your dining table. It was that big, and it needed water cooling and so on. Whereas Tim, for the first time, took a little semiconductor diode and successfully pumped the fiber with that. The following year, other groups did amplifiers with far better performance, and that was because Tim pumped at a wavelength of 850 nanometers, and erbium's actually pretty inefficient there. Quite a lot of the pumped light gets converted to green light, which, if you're trying to make an optical amplifier, is wasteful. But we did later exploit that to make green fiber lasers, and our former colleague Jenny Massicott there agreed I could use this photograph, which was absolutely everywhere when I first joined, of Jenny doing an erbium green fiber laser. But erbium fiber amplifiers are now widely used in our intercity networks, and yeah, that's another key development. It was moved from the lab to being commercial quite quickly. So I think 3 or 4 years later, Colin Miller and Paul Wheatley here were runner-up in the Prince of Wales Award for Innovation, and spent some time at Sandringham filming a piece for Tomorrow's World, all about it. So yeah, another good example of innovation being downstream very quickly. So we have now the components for the sort of systems we build our network from today. This is a WDM line system, wavelength division multiplexing. So the idea here is you've got a bunch of transmitters. They're now at very well defined wavelengths. We combine them together with a passive filter, think of it like a prism operating in reverse, go into an erbium fiber amplifier to boost the signals, then go to the far end and then do the reverse. So that's a fixed point-to-point line system. I was involved in the first deployment of that BT in the late 90s, and we still use that sort of technology today in the outermost reaches of our network. But in the core, we do something more advanced, where we optically switch wavelengths through the network. So in getting from Edinburgh to London, the signal remains all optical. So it passes through, if you like, optical roundabouts, Manchester, Birmingham, and so on. And that concept was first proposed at a conference in 1988 by Gough Hill of BT Labs. The idea of having a managed switched wavelength network, switching wavelengths around the network. And we then went on to lead an EU project called MWTN from 92 to 95, working with 9 other partners, which demonstrated in Sweden the world first managed optical network, switched optical network. The race program ran for a decade, and this project won an award in keeping with its significance. And again, this technique is widely used today. Okay, now turning to the very long systems, subsea. I could have said there are several BT milestones in subsea technology, but the one I'm going to talk about is TAT8, which was the first transatlantic subsea fibre cable. Went into service in 1988, 280 megabits per second. So there had been regenerators in those days. It was at 1310 nanometers. There were no urban fibre amplifiers in this. And this was kind of a three-way project. So the Americans did that bit, and then here was a branching unit. So the Marlton team were heavily involved in the design of that, which is non-trivial. And then one bit went up to the UK and one to France. But the amazing story here is that the only people who could make the ASICs for the receivers were Martlesham. The vendors couldn't do it. So all of that was, you can see the pictures on the right there, designed, manufactured at Martlesham, and that went into the repeaters. So this won another Queen's Award. So 2,700 of these things were manufactured at Martlesham and went in subsea cable systems all around the world. Okay, so from very long distances to very short distances. So quite early on, people started saying, okay, well, what about putting optical fibre to people's homes? So the first evidence I found of that was in Milton Keynes. Lots happens in Milton Keynes, where we ran something called a fibre vision cable TV trial. So that 18 homes delivered TV over point-to-point multi-mode fibres. And I got this certificate from a former colleague and neighbour of mine, did the splicing on it. So that was the world first deployment, but that was point-to-point fibre. And when it came to deploy fibre to the home in volume, that wasn't how it was done, because you imagine millions of homes connecting into exchanges, each with their own fibre. It'd be an enormous amount of fibre. So the idea of a passive optical network was developed at Martlesham. Various people in the front rows involved in that. The earliest paper I found on that so far, but I think there might be one or two a bit earlier, was from 1987. So the picture on the left here shows quite nicely the concept. So you've got your telephone exchange here, you have one fibre coming out, then you have a passive splitter in the street, which then sends a dedicated fibre to each of your customers. You share the bandwidth on this fibre amongst multiple customers. This is totally passive. That's it. So the first deployment of this in BT was in Bishop Stortford in 1991. And of course, the only service at the time was telephony. So it was telephony PON. I think it was 20 megabits shared the bandwidth amongst all the customers. Again, there's still some of that out there. A very forward-thinking aspect of it was that the idea was there to reserve a wavelength of light to later come along and add the broadband on top of the telephony. And I'll come back to that. But when BT launched broadband in 2000, didn't do fibre to the premises. Why was that? Well, partly, of course, it was this £15 billion cost that was always spoken about. You need money to come back in to justify that. I think early on, our license didn't allow us to do video. But even then, it's a hard business case to make. How much are people going to be prepared to pay? That was the problem. Meanwhile, another parallel piece of brilliant innovation was going on, and that was to squeeze more and more bandwidth along the copper pairs, DSL technology. Thank you to Kevin for this slide, which shows that through the 80s, 90s, and 2000s, DSL technology squeezing more and more bandwidth along the telephony pairs was really coming on leaps and bounds. And so for the first 15 or so years of this century, that's probably how your broadband was delivered. So ADSL first gave us 8 megabits, and then ADSL 2 plus gave us 24. Then along came VDSL 2, which took the fibre now to the cabinets, but still used the copper pair for the final bit. So amazing innovation, and it meant that enormous spend needed to do fibre to the home could be deferred. But we have now got there. So as I said, OpenReach are deploying PON and have passed 20 million homes. Other companies are deploying PON as well. So here a bit the basic idea, and this idea from the 1980s of reserving a wavelength for future use is in there, and partly it's in there because BT, while all the copper was being deployed, BT weren't sitting on their hands about PONs. So we're getting very involved. Jeff over there in setting up an organisation called FSAN to collaborate with all the other big operators and start to standardize on equipment to bring its cost down. And there are now a plethora of these standards for multi-generations of ponds. So about 10 years or so, I went along to that, and Derek, wherever he is, has been involved as well. So firstly, there was GPond, which is 2.5 gigabits downstream, shared amongst 32 customers. And then we reserved some wavelengths so that at a later point, you could come in and add the 10 gigabit pond along the same fiber. So all you really need to do is change the box at the ends. And in fact, last week, ECOC, I saw 3 generations of pond equipment where the head end equipment was all in a little thing about the size of a finger. So absolutely amazing. One final thing, you've got to get the fiber into the ground for all of this. So another great bit of innovation was blown fiber. So in 1982, Mick Reeve in the photo on the left, and Steve Cassidy sitting there, who I cannot for the life of me find a photo of, were investigating ways to install fiber in ducts without putting it under strain. And so they tried blowing the fiber in along a tube with air by attaching a parachute at the end. And it worked, but it worked even better when the parachute dropped out at the end, which you wouldn't expect. And so they went off to the library and learned about something called viscous drag, did some physics, and understood that basically the fiber was being carried along the tube on a cushion of air and under no strain. So a great, this is just a wonderful example of somebody having a good idea and it getting commercialized. So patents followed. There was a field trial in Leeds in '84, licensing to suppliers. It was used in Bishop Stortford and is now widely used by Openreach. If you're out in the street, and others, I dare say, and if you're out in the street and you see some people deploying fibre in the ground, chances are they'll be using this. So quite rightly, this won another Queen's Award in 1994. So final 2 slides. What happens next? What about 2030 plus? Well, as far as the ponds are concerned, I've already said they're very future-proof. What about in my current world, which is the intercity network? So we currently have our core network. We're moving from 100 gigabit per second wavelengths to 400 gigabit per second. A gigabit is 1,000 megabits per second. And I've got a line of sight to taking that to 800 gigabits. But beyond that, we do start to run into physics. So the spectral window of the urban fiber amplifiers, we're starting to fill it up. So 2 years ago, if you look at the spectrum on a WDM system, it looked like this with gaps in between the adjacent channels. But as they get faster and faster and faster, the signals broaden. So we're essentially getting close to the stage of filling all the available spectrum. So we're hitting something called the Shannon limit. So what happens next? So having come back from ECOC last week, I'm pretty comfortable that the world's doing plenty of innovation to allow us to squeeze more and more along the fibre. So multi-core fibres are being worked on, especially in Japan. The first one has been deployed on a subsea system between America and I think Taiwan. The hot topic there is something called hollow core fibre, which came out of Southampton University, and then Microsoft bought their startup. So this is a structure here. So the white lines are the silica glass. The black is just empty, really. So physics says that the only place the light can be guided is in this hole in the middle. So that offers all sorts of advantages: lower latency because the signal's not going through glass; it's going through free space essentially. They've also got the loss down. So since 1982, the loss of fibres has essentially been that 0.2 dBs per kilometre. Last week, the Chinese reported getting that down to 0.05 dBs per kilometre. And also it promises to support a much wider spectrum. So at the moment we work in the C band, which is where the urban fibre amplifiers work. But hollow core fibres promise to go much wider than that. And in parallel, I heard about people working on fibre amplifiers that work in some of these bands as well. So I don't lose a great deal of sleep about, there's no fundamental brick wall we're running into. The innovation will come and we'll be able to squeeze as much down a fibre as we need. The other big thing is really quantum networks. So quantum computers are looking very serious now. So fundamental questions about, well, how do you network those? So to sum up, going to quote John Midwinter, top left, who said that looking back, the period from 77 to 84, during which he was head of optical fibres, seemed like a golden age. I think he goes on to say that everything they tried to do just worked. When he left, he was given this rather wonderful leaving present, which his family allowed me to take a picture of, which was the coffin, and this had in it some of the preforms used to make the fibres, but also all of the technologies which were made obsolete by optical fibres. You can see a piece of this in there. But to sum up, there are some key technologies that make the internet possible and change the world: single mode fibre, semiconductor sources and detectors, optical amplifiers, coherent WDM, all optical switching, passive optical networks, blown fibre, all absolutely essential to the network that makes your interconnection work. And they were all pioneered at Martlesham, due to several people in the room. So thank you all. This is where they tell me what I got wrong.
It's a fascinating talk, Russell. Absolutely brilliant. We're going to take some questions now. We'll start with the audience here in the atrium, and then we'll go online. So for those online, if you have a question, please use the Q&A function in Teams. That's how we pick the questions up. So use Q&A, not chat. Right, the atrium. First question. Who would like to ask a question?
The subsea cables and things like that, the long distance fibre optic cables.
The experts on that are over there. So
oh, right, okay.
I'm getting ready to deflect the question.
Yeah, that's do you need to replace the fibres, or can you, when after a period of time, or can you just replace the optics and the electrical connection to get higher performance?
I think there's always been the dream that you could leave that expensive bit in, and just which is the fibre cable, and just change the edges. I think around about TAP 12 involved, that was being talked about adding extra wavelengths, I think, but certainly TAP 8, certainly I don't think that. Yeah, and the optical amplifier was key to that, I think. I mean, as long as you had repeaters in there, which you did for TAP 8, you'd have to rip the whole lot out. But I think I'm right in saying around about TAP 12 to 14, that sort of thing went on. But you've got your, I know a former colleague called Andrew Ellis, who might be on the call, but I don't know, said you never really make an optical system upgradable. You just basically don't use it at its full capacity at day one. So I don't, the current stuff, I'm not close enough to know to what extent they upgrade that without taking the cable.
Certainly in the early days, the systems became redundant before they wore out. Like TAT 8, it was only in service for a few years. But once the optical amplifiers came along, there were superior modulation techniques that would extend the capacity without ripping everything out.
For the benefit of the online audience, could you repeat that answer? No, could you repeat that answer?
Well, I think the summary was that's happened sometimes, but we don't think it has happened that often. So certainly not in the early days when regenerators were in there. I think optical amplified systems, I think it's happened TAP 12, TAP 14, I think it happened around about then. These days, I have no idea to what extent.
Thank you, Russell. Do we have any online questions? Or we could try and alternate.
There are no questions online at the moment,
okay.
And I will make a plea now to the 50 people online. If you do have a question, please raise it via the Q&A so that we can raise it to Russell.
We'll take another question in the atrium. Steve.
No, don't.
Sorry, Russell.
Go on then. I should say Steve's been a huge help with this presentation.
What I was going to say is really, I mean, great. And I know that you are a very cautious person, so you will not make a claim about your Martlesham contribution or BD's contribution or PO's contribution to this. But I just wanted to say that it is possibly not evidenced in that we don't have the paperwork, but from what I can find out, and there are other people who back me up for this, we actually paid predominantly for Charlie Cale's work.
I did say we funded him. I did say
we funded so like 90% of that work.
You think it's much of that?
STL put in a certain amount of money because he was their man, but it was not so much that BT picked up the result of his work. We drove him to do this because we believed that was the answer, and I think that's an important point. Really.
Yeah. I coached from Steve to be more bullish about this, which I thought I had been, but obviously still didn't quite get.
I'd like to add that not only did BT fund and drive the work at STL on fibre, it did it on lasers as well.
Right.
We'll take another question from the audience. Gentleman at the back.
Can you make any comment on fibre lifetimes?
Fibre lifetimes.
Perhaps you just repeat the question.
The question was, could I make any comment on fibre lifetimes? So I think the first fibre from 1982, I would put a fair amount of money is still in there working, right? There's little evidence that it sort of ages or anything like that. I think all that happens is it gets repaired over the years, and so you design your link budget to take account of a number of repairs and system lifetime, particularly in subsea. That's important. But even then, I'm struggling to think. I mean, we went on this stuff for 30 odd years. I can't think of a single example where a cable has been repaired often enough that the system no longer works because we used it for the lost budget. So we think of hydrogen. Is that what you're thinking of?
Just the crack growth in the glass, etc.
Yeah.
There are no known examples of that. I've googled it, but there are no known examples of actual spontaneous fibre break.
It's solid stuff.
The dominant feature is hydrogen getting into the cable. That brought down at least one submarine cable system.
I thought of mentioning hydrogen, but decided not to in the end.
Right. From online.
Okay.
I have one comment and one question.
Oh, another comment now.
So the comment is from Simon Harry of Nokia.
Oh yes.
And he asserts that Sienna and Nokia have had a very successful business upgrading 10 gig submarine systems to 50 gig, 100 gig, and 200 gig. Per wavelength. So that perhaps answers some of the other questions.
Thank you, Simon. I'll give you an easy time next time we're together.
And a question which might be an easy one, or it might not, from Sharon Indu Mathi, who asks, will fibre optics replace copper one day?
I got very careful.
No, you don't. Easy answer.
So the question basically is, will everybody either be on fibre to the home eventually, or radio? Because the thing is, the cost of doing fibre to the home sort of goes up a sort of hockey stick. So as you get to that final percent or whatever it is, it's always going to get phenomenally expensive. So I never say never, because you nearly always prove wrong. But 100% FTTP is probably a long way off. So when will we actually stop using copper?
It will happen. It has to happen because the copper network is uneconomic. As you've got too few copper pairs being used,
you've got to maintain them. Yes.
It goes through the roof per customer.
That's just the advantage of recovering the copper and then selling it.
The value of the copper is great.
Indeed. The copper will go, but I still think for the foreseeable future there'll still be that final, however many percent it is, it will probably be on radio. I suspect that's the answer. But I still think it's a long time till it all goes.
Another question from the audience.
Yeah, so I guess one of the jigsaw pieces that you haven't talked much about is the joining of the fibre and splicing. And I guess, we're up to cables with ribbon fibre with 1,600 fibres in a cable. Did BT play any part in the development of fusion splicing? And
absolutely.
Who did that?
My learning colleagues.
Would you like to tell us a bit about that? Because I find that fascinating.
I would defer to the people who did it.
joining by using electric arc to fuse the fibres together way back in, that was late 70s, definitely in the 70s. Yeah, it was more difficult with multiple. That was one advantage of a single mode, is it's easier to splice with fusion splicing, because all that dope you have to put into the causes bubbles. So you only get a bubble in that joint, and the loss goes through the loop. So you do have to get rid of that. And it made it much, although it's much more difficult to align, because you've got to get those cores very precisely aligned. But we specified, we talked about it, but the other thing that BT did was perform the specification. One of the parameters for that we specified was what we call the concentricity element. That is, how accurately can you put the core of the fibre in the middle of the fibre relative to the cladding. And then again, it comes back to physics. If it's in the middle, you can use surface tension to align the fibres when it's molten. And that's what we use. The Japanese decided not to go down that, interestingly, because whether or not they couldn't make good concentricity fibre, I'm not sure. They actually started to try and push the joint to line the fibres up on the cores and then fuse it. But I think everybody's now gone to cladding alignment, as we used to call it.
I said that as part of researching this, Openreach has showed me that they have, I think you're alluding to, ribbons of fibres that all get spliced at once. And it's just phenomenal.
Yeah.
And this is now done every day of the week.
Yeah.
And they also do it in dirty condition, which we said you should never do. I finally got fogged to the home after 40 years.
So let's take, thank you, Dave. Should we take an online question?
I have an online question which is testing your sense of humour here.
Oh dear, that might fail.
And it's from Scott Hill. He says, do you find it ironic that 3.2 terabits is now spawning a host of waveguide startups? And do you think there might be a speed limit for fibre above 1.6 terabits?
Absolutely not. Absolutely not. I mean, the vendors I talk to, 1.6 terabits per wavelength is it can't reach the length of the country, but you can go useful distances with that. So absolutely not. And then the new things I was talking about, the hollow core and so on. So no, we've not reached any sort of brick wall.
You couldn't be clearer.
No, crystal clear on that. Sorry.
What about the irony then?
Do we have another question from the audience in the atrium? Gentleman at the back.
I work on Openreach at the moment. We look at the GPON network, see XGS as well.
Mm-hmm.
But where do you see which PON technology beyond XGS taking off? See this 25 gig, 50.
So we've got Derek somewhere. I think the world's landed on 50.
So Russell, I think we just need to
Repeat the question. So the question was coming from someone from Openreach. So we have GPON today. We have XGS PON, which is 10 gig PON. What comes next? And I've only been on the edge of this for the last decade or so. Derek's been close, but I think there was a bit of a debate. Well, there was a debate going for quite a while. Was it 25 or 50? But I think that's landed on 50, and you're now working on 200.
In ITU it's 50, and China's going 50, so that's
So it's 50.
generally the market. And then yeah, we are just starting to.
Could you repeat that?
Yeah. So
For the microphone, sorry.
Derek, maybe just shout up.
yeah, it's all right.
No, I guess we need it for the people online.
Yeah. So the answer was that there was a debate in recent years about whether the next step from 10 gig would be 25 or 50. But both the ITU standard and the China market, which of course is very important, have landed on 50, and the standards are now starting to work on 200 gigabits, which I assume is coherent. I've never looked at it at all, but that's still being kicked around. Is it? Right. Yeah.
And 50, just to be clear, that is now already being deployed. It's not coming. It's already there.
So again, there's no sign of any bottleneck or anything here. The technology is still moving.
George, any more questions on
I have a question from Peter Straddons, who notes that you mentioned approaching the Shannon limit, but is there scope to achieve higher transmission rates by research aimed at reducing signal to noise ratios? Are we already as good as it gets in this area?
So I think we're getting the amplifiers are pretty good in that respect. So I think the most fruitful way is going to more spectrum. I'm sure that's the dimension that will be explored next, because we're only really working in quite a narrow bit of the spectrum. The EDFAs work from 1530 to 1565 nanometers. The fibers are reasonably low loss, so broader than that. And as I said, the hollow core fibers will be low, talking about being lower loss in a much flatter way. So spectrum first.
Okay, thank you. Any more questions from the atrium? The audience? Gentleman at the back.
This sounds down trouble to me.
I wasn't aware quite how good the hollow core transmission loss got. How difficult?
So the question was how the loss of hollow core fibre. I said it last week. It was reported at 0.05 dBs per kilometre. I'd never made one, but I am reliably informed it's pretty hard, right? So it's not. You know, its cost points are not yet at the standard stuff that we've been putting in for the last 40 odd years. That's not to say it'll never get there, because you know, if you chuck volume, if there's a wheel and you throw volume at something, then you do amazing things. I think the PON experience tells us that. Yeah.
Thank you, Russell. George, any more questions from online?
I think we are finished on questions online.
Online, okay. Any more questions from the audience here in the atrium? No? Okay, right, well, please join me in thanking Russell for a great talk and taking the question. I've just got the tail bits to do, just the so for the audience here in the atrium, thank you very much for your attendance, and online I think we had about 52 people, something like that online, so thank you very much for your participation. I just want to plug our future events. Our next event is going to be on the 6th of November, and that's going to be a hybrid event as well. And that's going to be on point-to-point microwave systems by Professor Andy Sutton, who is also from BT and is a BT fellow. So that's our next event. That'll be at the atrium here. The committee is planning a pretty extensive program of events. We try and have an event every month. I know we've got one lined up for December and January, February as well, and March and April, pretty much every month. I'm not listing those at the moment because they're not open for registration, but they will be open fairly soon. And if you keep an eye on our website, our IET EngX website, there's the link there, or there's a QR code over there. You can scan it on your phone. Keep an eye on the website. There's a pretty interesting program of events that we've got, and also visits for the rest of 2025 and 2026. So would encourage you to take a look at that. As I mentioned earlier, CPD certificate will be done as quickly as we can. We have made a recording of Russell's talk, and we will, with his permission, upload that to our website. But we need to do the editing on the video recording, taking off the introductory bit and some of the end bits. But we need to do that with that post-processing. So it will take a week or two before we can do that. I think that's really all I wanted to say. Again, once again, Russell, thank you for a great talk. It was a halcyon days of fibre development at BT Labs. Fascinating, and it was great to be there as well, watching the fibre story unfold from a copper person. We did our best, but we couldn't get anywhere close to the fibre speeds. So thank you very much. I'll close the meeting now, and for those online, you can disconnect now. So thank you.